I've decided I'm going to do something for the AP exam season. I'm going to do physics instead of math, which is what I usually want to do. And the reason is physics has math in it, so that's that's a plus. But also, lots of people, and it doesn't just apply to the high school students. It also applies to the college students. They have a lot of struggle in physics, and a lot of the physics concepts that you learn has a lot of math under it. And if you struggle in math, you're definitely going to struggle in physics because it's math but word problems and it's applied, so it's way worse. So that's why I want to make the physics review. And we're going to start off by covering kinematics, which is the first topic of today. First topic of most college courses in the first year of physics. Now, I'm mostly going to be covering AP Physics 1 material and AP Physics C material for mechanics and electricity and magnetism. That's why it's going to be red if it's calculus based. Now, most of you are taking calculus based, but even in calculus based courses, there is a lot of emphasis on algebra, like the algebra method to solve problems, and a lot of deriving formulas comes from algebra. So let's derive our first formulas. So here I have this is supposed to be a review, so I'm not supposed to explain too much, but I might over explain. Also, if the audio ever goes bad, then I am sorry, but I can't really do anything about it. So here we have a graph of v of t. What's the equation of this graph? Well, assuming that this point right here is the initial velocity, which is, I will say v naught right here, we'd have the equation v equals v naught, right, v of t, or I say v of t, which is, in this case I'd say v is equal to v naught, initial velocity, plus the change in velocity, or the change in time over the change in velocity, change in velocity over change in time, times time. And that is your equation. That's your first kinematic equation. It's v naught plus change in velocity over change in time is acceleration, average acceleration, times time. So this is your first equation right here. So first velocity equals final velocity equals initial velocity plus accelerated time. Now, we could also calculate the area under a curve. The area under this line, actually, is what you would say. And even if you don't understand calculus, you'll see where this comes from. So if we calculate the area under this line, let's say from t, let's say from like this change in, I'm going to say this is change in time, or if we assume that this time is 0, this is t equals 0, then this width would simply just be time, t. Now, this is a trapezoid. The shape is a trapezoid or a trapezium. So, in order to calculate the area of a trapezoid, we can either separate it into to a rectangle and a triangle, or we can combine them, and we can just take the two widths, take the two heights in this case, and multiply by their width, which is t. So that's what I'm going to do. So t over 2, like this, equals, what's going to be on the left side? I don't know. We'll figure it out. But in this case, actually, it's not really a great idea to figure out them separately. I'm gonna do it anyways. So what's this first thing right here? This first width is v naught, because this is the initial velocity. So this is a height, right? So this will also be v naught, v0. Now what's this right here? What's this right here? This is actually, this height is the change in velocity. Yeah, that's the height is the change in velocity. That's how you get this. This height is the v minus v naught. Or I could put that down as well. So v minus v naught. And if we do v minus v naught like this, what do we get? We get v minus v naught. If we substitute this v in here, we'll get v naught plus at minus v naught, which is just at. And that kind of makes sense because it's the slope multiplied by the x value, right? The slope multiplied by the x value. Now, v naught has units, meters per second, which is some of the SI units that we're going to use. V naught has units, meters, which is the SI unit for distance, per second, and time has a unit of seconds. So if we take meters per second, if we want to find the area of this, and we take meters per second times seconds, what are we going to get? Meters per second times seconds equals meters. So this will be something with meters in it. I'm just going to use S. So change in S, or just S in general. But change in S is equal to what? It's equal to, let's see. It's equal to V naught plus V naught plus AT divided by 2, all divided by 2, right? So V naught plus AT, all divided by 2 times the time, which is equal to V naught T. This is 2 V naught over 2 times T, V naught T plus 1/2 AT squared. And this is your second kinematics equation. Now we could do we could do other kinematics equations. We could continue with the third, fourth, and the fifth. In fact, I will do that right now. I'll do it really quick. So this is our second one. Our third one is if we wanted to find V. So what I do is just move V naught right, or I could subtract AT, and what I get is V naught equals V minus AT. Which is not the different equation, but if we want a equation without V naught, then it'll just be delta S equals V minus AT times T plus 1/2 AT squared, which will give you VT. So final velocity is time. Final velocity minus AT squared plus 1/2 AT squared. So if you take your final velocity, it will be VT minus 1/2 AT squared instead. So that's your third kinematics equation. That's usually the kinematics equation that no one uses. Or no textbook shows you. You are not going to get the kinematics equation like this in any textbook. Now what do we want to remove? Let's say we want to remove acceleration now. Okay, so we'll use this equation. We'll use this first equation. We want to remove acceleration. So let's solve for this first equation to see if we can have something that will remove the acceleration. So acceleration is equal to, from this equation, acceleration is equal to V minus V naught over T. So we can substitute that into our first equation. We get V naught T plus 1/2 times V minus V naught over T. Right, V minus V naught over T times T squared. What will that give you? That will give you 1/2 times V minus V naught T. So I'm just gonna skip a little bit. 1/2 V T minus 1/2 V naught T. So we have 1 V naught T minus 1/2 V naught T. What we'll get is 1/2 V naught T plus 1/2 VT is equal to delta S. And that is the fourth kinematics equation. And I will write that simpler. Oh gosh, I need to charge my computer. I will write that simpler I will write that as, or maybe you think it's a little bit more complicated for me to write this, as this, but I think it's simpler. So let's do. Oh God, sorry. Let's move this up here, and let's make it 1/2, or I'd say t over 2 times v plus v naught. That's the fourth kinematics equation. The fifth kinematics equation is I say it's the most useful, but it's really hard. It's really quite hard to get, right? And the fifth kinematics equation does not rely on time. So let's solve for time to see if we can get that kinematics equation right now. So v minus v naught over a is equal to time. So I'm just going to say time is equal to v minus v naught over a. And instead of substituting into any of these equations, I don't want to do v naught times v minus v naught. So I'm just going to do this equation. It's a lot simpler because we could actually use something called difference of squares. So t over 2 will actually become v minus v naught over 2a, like this, times v plus v naught. And I'm just actually, oh, I'm sorry, it's going to be a little bit loud. This will become v squared minus v naught squared over 2a. So delta s. So then we can say that 2a delta s equals v squared minus v naught squared. That is your last kinematics equations. That is all the kinematics equations you will ever need to know, and each of them has one component missing. You will have the initial velocity, the final velocity, the initial velocity, the final velocity, the time, the displacement, and the acceleration. This only works if it's constant acceleration. I cannot emphasize that enough. Only works if it's constant acceleration. If it's not, it will not work at all. It will not work if there's no constant acceleration. You get some wacky stuff. This is assuming that there's constant acceleration, so all of these work. Which is like this velocity, linear velocity increase, corresponds to a constant acceleration. If there was no linear velocity increase, we would have to use derivatives, which comes in the formulas v equals ds over dt. So velocity is the derivative of displacement, and a is equal to dv over dt, which is the derivative of velocity, which is also the second derivative of the displacement. So that's how it works. Okay, this is how it works. Only two formulas you need to know if it's nonlinear, but most of the time they won't give you the formulas, the rules for s of t, v of t, or a of t. So this is only assuming that v of t is linear and a is constant, of course. So first example, velocity time graph for an object moving along the x-axis is like that. Plot a graph of acceleration versus time. This is pretty conceptual. Acceleration is the change in velocity over the change in time. So I will actually just put use a different color, let's say blue, so a of x, right? And I'm just gonna draw a of x over here. So for the first 5 seconds, nothing happens. First 5 seconds it's moving at a constant velocity. Since it's moving at a constant velocity, it's not speeding up or slowing down, so it is not accelerating. So the acceleration is 0 meters per second per second. Now, saying the meters per second out, this is in units meters per second per second. Saying this out means that it's changing at whatever meters per second. So the velocity in this case is changing at 0 meters per second, not changing every second. So it's not changing every second. However, if we go up here to -8, this this kind of area, I'm just gonna assume that this is -8, -5, or I'm sorry, +5, -8, and this area is not +5, -8. This area is 15, 8. We will use the equation. We will use the slope formula in this case because it is changing. It is now changing at a certain meters per second every second, right? There's 10 seconds down here, and how many meters per second has it changed? It's changed from -8 meters per second to 8 meters per second. So that's a difference of 16. 16 divided by 10 is 1.6 meters per second per second. So the velocity is changing at 1.6 meters per second. So I'm just going to assume that it's like something like right here. I'm not going to be able to draw a straight line, I'm sorry. Like right there. It'll kind of be an asymptote right here, or maybe like pretty steep, because it looks continuous right here. It still looks differentiable, but 1.6 meters per second, and then it goes back down to 0 meters per second. And I'm gonna stop saying meters per second because in physics we just simplify it to meters per second times 1 over second, which is meters per second squared. So it's 1.6 meters per second squared. It's changing at 1.6 meters per second every second. That's the definition of acceleration, is speeding up or slowing down. So determine the average acceleration in the time 5 to 15, already did, and in the time 0 to 20. So the average acceleration in the time 0 to 20 means we have to take what our velocity is at 0, what our velocity is at 20, and subtract them, or divide them, I'm sorry. So velocity, well, no, actually, yes, subtract them. So what our velocity is at 0, it's still 8. So it's still 8 minus -8. And then in this case, the time is 20. Time at 0 is 20, and then the time at -8 is 0, which is 0.8 meters per second squared. So it's changing on average, not definitely, not at any like moment, not at any particular moment. It's not changing at 0.8 meters per second for most of the trip, but on average it's changing at 0.8 meters per second every second. Okay, let's go to the next one. Electron in a cathode ray accelerates uniformly from 2 times 10 to the 4 meters per second to 6 million meters per second over 1.5 centimeters. A, in what time interval does the electron travel this 1.5 centimeters? And B, what's the acceleration? So what is missing? Well, first of all, what do we have? So V naught is 2 times 10 to the 4 meters per second. V is 6 times 10 to the 6 meters per second. And our distance, delta S, is 1.5 centimeters, which I want to convert to meters. 0.015 meters. This is assuming 1 meter is 100 centimeters, which I don't actually have to assume. It's a human construct. It's just 0.015 meters. So what equation do we use if we want to find the time interval? We use, right here, we use this fourth equation. This is our fourth equation. We use this equation. So it will become 0.015, or I'm going to write down the equation. So it will become 0.015 equals time over 2 times 6 times 10 to the 6 plus 2 times 10 to the 4. And if you multiply this out, you will get t is equal to, or I'm just going to put it at the bottom, t is equal to 0.03 over 6 times 10 to the 6 plus 2 times 10 to the 4 seconds, which is, I'm going to need to pull my calculator out. Give me a minute. This should be around 30 microseconds, I think. Should be around 30 microseconds. So let's see, 0.03 divided by 6 times 10 to the 6 plus 2 times 10 to the 4 is not 30 microseconds. It is 5 nanoseconds, which is I'm just going to say 4.98 times 10 to the negative 9 seconds. Very nice. Now what's the acceleration? Now we have 4 quantities. We can use any of the formulas that has acceleration in it to find acceleration, but let's just assume that we don't have the time. So what formula we'll use? We will use this fifth formula right here. 2a delta s equals v squared minus v0 squared. So that's going to be huge, right? So 2a delta s is equal to v squared minus v0 squared. Our delta s is 0.015, so 0.03a is equal to, oh gosh, that's a massive number, 6 times 10 to the 6 squared minus 2 times 10 to the 4th squared. So a is equal to that divided by 0.03, right? Which is, let me just calculate that real quick. So 6 times 10 to the 6th square minus 2 times 10 to the 4th squared, and then divide that by 0.03 is 1.2 times 10 to the 15 meters per second squared. So this electron is accelerating at this 1.2 times 10 to the 15 meters per second every second, which is, if it's accelerating like that for 1 second, that means it's traveling faster than the speed of light, which is crazy. But if it's traveling for so little time, it's only traveling for 5 nanoseconds. So if it's traveling for this little amount of time, then the acceleration can, like, you don't have to, you can assume that it's average. You can assume that it's traveling at a linear constant speed. However, if it's traveling for like any longer than, I'd say, any longer than 1 microsecond, we'd have to account for relativistic corrections. We'd have to make sure that the electron isn't breaking any laws of physics, or we aren't breaking any laws of physics by calculating it like this, instead of with other methods that are a lot more advanced for this first year of general physics course. So let's go to the next one. The minimum distance required to stop a car moving at this is 40 feet. So stopping a car, this is a little bit harder to find out all the information. Also the units are different, which is annoying. Really, really annoying. But we can use the fact that 1 mile is equal to 5,280 feet. Right? That's kind of arbitrary, but we can use that fact. So let's see. We can solve this 2 ways. I'm going to solve it for the first way. Since this book that I'm using has black, blue, and red problems. We're not going to do any red problems today. But black problems are basically problems that are basic, blue problems are intermediate, and red problems are advanced, or like hard. So black problems right here that we have, this can be solved using only numbers. So let's do that. Let's solve it using only numbers, and I'll solve it a different method this time. I'll solve it 2 methods. I'll solve one using numbers, one using variables, but we have a, right, so we have a the minimum distance required to stop a car moving at 35 meters 35 miles per hour is 40 feet. So our v is 0 because it stopped. V0, V0 is 35 miles per hour. 35 miles per hour. And the acceleration is, we don't know the acceleration. The time, no, the distance, delta S, is 40 feet. Now, the acceleration is assumed to be the same rate. Because the acceleration is assumed to be the same rate, let's find the acceleration so that we could use that same acceleration for the next part of our problem. So what will it be? First of all, we got to find 40 feet in terms of miles. So 40 divided by 5280 is 0.00757 or 758 miles. So let's do that. Let's do v squared minus v naught squared is equal to 2a delta s. Let's see what we get, right? So our v naught squared, our v naught is 35 miles per hour, so 1,225 negative is equal to 2 times a times 0.00758. Pretty low. 1,225 divided by 0.00758 times 2. That is a really big number. But it doesn't matter that it's a big number because it's miles per hour squared, not miles per second squared. So it's miles, negative 80,804 miles per hour squared. That's our, that's a very, very scuffed measurement, but it's valid. So that's our acceleration. Now we have our acceleration. Negative, or actually, this might be a little bit confusing because we'll be using h later. So miles per hour squared, like this. Now our v is still 0. Our v naught is 70 now. Our delta s doesn't matter. Our delta s is chilling. Our delta s we need to find. But we have our a. And I'm not gonna transport the a. I'm just gonna leave it down there. Using the same formula, we'll get v squared, which is 0. So I'm just gonna leave that there. So negative 70 squared is equal to 2 times negative 80,804, or 805 if you round, 804 if you truncate, times delta s. So let's see, negative 70 squared divided by negative 160,000, or negative 2 times negative 80,000, or no, positive 80,000, or 2 times negative 80,804 will give you delta S is equal to 0.030232 miles, which if you multiply by 5280, you will get 160.09 feet. Since this problem is 3 significant digits, we just shortened it to 160 feet. This is one way of solving it. There is another way of solving it. It's actually, I'd say it's easier. So let's try to solve it that other way. In fact, this other way that we solve it, we're not even gonna, it would make this a blue problem, which is intermediate. This other way of solving it, I'm just gonna leave everything here as is. So v is 0, and if v naught is, I'm just gonna say v naught is v naught, and delta s is 40 feet. then we'd have v squared, 0 squared, minus v naught squared is equal to 2a times delta s. Delta s is 40 feet. So whatever a is equal to negative v naught squared over 80 feet. Feet per whatever, it doesn't really matter. We go for the unit at the end. So a is just equal to v naught squared over 80, and it's negative because it's slowing down. So if we do the thing again, v equals 0, but v now equal to 2v naught because, well, the second speed is double the first speed. So what would our delta s be? So it would be v squared equals 2v naught, or I'm sorry, v squared minus 2v naught all squared, right, is equal to 2 times negative v naught squared over 80 times delta s. So v squared is 0. That's sometimes what I'll do. I'll just cross it and then I'll put 0 on top because we know it's 0. The negatives will cancel. So what we'll get is 4v naught squared is equal to 2v naught over 80. Or 2v naught squared over 80 times delta s. V naught squared can cancel. 2 over 80 is 1 over 40. But we can multiply by 80 over 2 on both sides. We'll get 160 equals delta s. And obviously it's feet. So that is our right answer. Right? So sometimes working through the problem without all those numbers and just having variables instead of the numbers is an easier way, because there's some very nice cancellations that will come out and you will get this result. You don't even have to use 40. You could just use delta s, right? Delta s equals delta s. You'll find out that your final answer would be 4 delta s initial, which will give you 160 feet. Now examples 4 through 6. These are all examples of just me applying the formulas that I've already told you to solve the problem. So it'll just be really quick. Acceleration, or starts from rest, so v naught 0. Acceleration at 2 meters per second squared, positive, until it reaches a speed of 20 meters per second. So that's scenario 1. Scenario 2 is the truck travels at 20 seconds, for 20 seconds at constant speed until the brakes are applied. So since he's traveling at 20 seconds at constant speed, our v naught is 20, and our v is 20. Which is a little bit weird. So we can just say, just in general, that v is equal to 20. And this doesn't have anything to do with v naught or v. Stopping the truck in a uniform manner in an additional 5 seconds. Wait. Yeah. Okay, so I just say v is equal to 20. And then stopping the truck in a uniform manner. So the stopping motion would be a second equation now. So v naught this time will be the 20 meters per second. V will be 0. And our acceleration, we don't know yet. Our time is 5 seconds. So these are 3 separate scenarios. How long is the truck in motion? The truck, how long was the truck in motion? The truck was in motion for, well, we gotta find our times. So what's the time that it took to do this? We could use our first equation, because our first equation has v naught, v, a, and time. So v naught, or I could say v20 equals v naught 0 plus at. So plus a times the time. So time will be 10 seconds. 10 seconds, the problem says 20 seconds, and it takes 5 seconds. So a would be 35 seconds. 20 plus 10 plus 5 is 35. What's the average velocity of the truck for the motion described? Now, this is definitely going to be a little bit hard. But to find average velocity, or not the change in velocity, to find average velocity, we have to take the change in acceleration over, oh, wait, no, I'm sorry, that's wrong. That's 100% wrong. We have to take the change in position over the change in time. So the total change in position over the total change in time. And the total change in time is 35. We know that. What's the change in position? We have no idea. No idea what the change in position is. Let's find out. We have V naught, V, A, and delta S. But in fact, I don't want to use that equation because it takes too long. So I'll just use instead the fourth equation, which is V naught plus V times T over 2. So delta S is T over 2 times V naught plus V, which is T over 2 is 5 seconds, times V naught plus V is 20 meters per second, so 100 meters. 100 meters. In this case, V equals 20, and it's traveling for 20 seconds, so distance is equal to speed times time, so delta S in this case is 400 meters. We could also use the fourth equation, saying that V naught is 20 and V is also 20. And V naught in this case 20, V is 0 times 5 seconds, so we could use the equation again. Delta S equals T over 2 times V naught plus V, which is 50 meters. So our total distance traveled is 550 meters over 35 seconds. So our average velocity is 550 divided by 35, 15.71. Or 15.7 meters per second. And that's your answer. Pretty comprehensive review of all of those formulas. But let me just erase these real quick, erase the work real quick, and I will go on to the next question. The next question, why is the following situation impossible? The following situation is starting from rest, a charging rhinoceros moves 50 meters in a straight line in 10 seconds. And her acceleration is constant during the entire motion. And her final speed is 8 meters per second. So let's see why it's impossible. So we have our delta S 50 meters, our V final is 8 meters per second. Our V initial, or actually I'm just gonna say V, just V. V is 8 meters per second. V initial is 0, and our time is 10 seconds. We have all four quantities, but we have to disprove why the acceleration is not constant. If the acceleration is constant, we have to disprove why the acceleration is constant. If we want to do that, we have to use our equations, because the acceleration's constant means we should use our equations. Our equations are good for when the acceleration is constant. But our acceleration has to be the same for all of the equations that we use. So let's use our fourth equation. That's my favorite. Except for the fact that it doesn't have acceleration, so I can't actually use the fourth equation. Never mind. Let's use our our fifth equation, v squared, right? So 64, or v squared minus v naught squared equals 2a delta s. I don't know what a is, but we definitely know what delta s is. 100a equals 64, so a is equal to 64 over 100 meters per second squared. Now we'll use another one of the equations. Let's use v naught t minus 1/2 at squared, or plus 1/2 at squared, I'm sorry. So 50 is equal to, v naught is 0, so we can, right, I could do v naught t, and then I could cross it, put 0, plus 1/2 at squared. So what's our t? Our t is 10 squared, right? So 10 squared is 100. divided by 2 is 50, so 50 equals 50a, and then a equals 1 meters per second squared. We have two different answers. Acceleration can't be two different answers if the acceleration is constant. It has to be the same acceleration for the whole thing. So, for that reason, we have disproved that it's not possible. So let me erase everything except for the fact that the two accelerations are different. So we have proven now that it's not possible for the rhinoceros to move at a constant acceleration because our accelerations are different. So ac are different. Next question. Driver of the car brake when he sees a tree blocking the road. Car slows down uniformly. This for this amount of time, making straight skid marks this much long, all the way to the tree. With what speed does the car then strike the tree? So we know that our v final is not going to be 0, but our v initial is we don't know either, actually. So we're not going to put down our v initial. We're going to put down time is equal to 4.2 seconds. We're going to put down acceleration is equal to minus 5.6 meters per second squared. And we're going to put out delta S is equal to 62.4 meters. Now, we have all of the quantities that we have for equation 3. So let me give right here, equation 3, vt minus 1/2 at squared. So let's use that. Delta S is equal to vt minus 1/2 at squared. And I'm going to solve for v, so I don't have to put everything into an equation. So I don't have to put numbers down, and it's going to take too long. So v is equal to delta S plus 1/2 at squared over t, which is equal to, let's see, delta S is 62.4 plus 1/2 times A is negative 5.6 times 4.2 squared, right, divided by the time, which is 4.2. So our final velocity is 3.097 meters per second, or 3.10 meters per second. So yeah, when you bump a car, sometimes you don't have enough time to stop the car in time, so you will end up having a little bit of damage on your car if you don't stop the car in time, especially in traffic. You'll bump the car in front of you with a certain velocity, and you can calculate that velocity like this. Usually the acceleration is constant because there is a maximum that your car can brake, and if you use that maximum the entire time, then the force applied will be maximum. And if we go to the next review, or you've studied in your course, the force and the acceleration are proportional. So if you apply a constant force, a constant acceleration will happen, right? Next, I'm actually not going to do this. This is a waste of time. It is possible to shoot an arrow as high as 100 meters per second. How high would an arrow launched at this speed rise if shot straight up? So now we're moving on to vertical kinematics, vertical acceleration. And vertical, when we take into account up down, there is always the same acceleration. It's called g, which stands for gravitational constant. And on Earth, if you are close enough to the atmosphere of Earth, it is always negative 9.81 meters per second. But we're going to use, negative 9.81 meters per second squared, but we're going to use negative 9.8 meters per second squared, which is usually what people use. You can also use negative 10 meters per second squared on the AP exam. It is totally valid, but I'm going to use negative 9.8 to make my life harder. Negative 10 will make the equations really, really simple. But anyways, so it looks like it's not giving you that much information in 49, but it is giving you the acceleration already automatically. So if friction can be ignored, how high would an arrow launch at this speed be rising if shot straight up? So if it's reaching its height, what is the final velocity? If it's reaching its height, what would be the final velocity? The final velocity would be 0, because after that, it will be going down, right? So if it's reaching its maximum height, it's going to be still increasing, right? Still increasing up until it's reached its point, and then it will start to go down. So at its maximum height, its velocity in the y direction at least is 0. If we have our g, we can obviously use the delta s. We can obviously use that function. We want our distance, or in this case, I'd say delta y, because it's the change in the vertical displacement. So v squared minus v naught squared, v squared minus v naught squared minus 10,000 is equal to 2 times a times delta s, which will be, well, negative 10,000 divided by, this is 510 meters. 510 meters. How long will the arrow be in the air? We could use v naught t minus 1/2 at squared, but since we already have delta s, I like to use the fourth equation, so let's use the fourth equation instead. 510 is equal to the average of 250, or 100. Yeah, we could do v plus v naught over 2 times the time. So the time will be approximately 10.2 seconds. Approximately 10.2 seconds. And that's your first question. Next question. The height of a helicopter above the ground is given by that function, 3 times t cubed, where h is in meters and t is in seconds. At t equals 2, the helicopter released a small mailbag. How long after it's released does the mailbag reach the ground? So we have our g is 9.8 meters per second squared. I'm just going to put g as g from now on. I'm not going to put the negative 9.8 meters per second squared. It takes too long. So let's see what the first height is. The height of the mailbag at its initial launch. So 3 times 2 cubed is h of 2 is 3 times 2 cubed, which is 24 meters. So that's our delta y. It's 24 meters. Or actually, our delta y is y final minus y initial. So it's actually negative 24 meters, because eventually our package is going to be on the ground. Our g is g. Our v our v naught. So the initial time, it's just going to be a release. It's not going to be a throw with an initial velocity, just a release. So our v naught is 0. Our g is g, and we want to find time. So our g is g. So we have these 3 components, or if you're confused, you can say delta s is right here. So what equation will we use? We will use the second equation. The second equation is delta s, or delta y, negative 24 meters, is equal to v naught times t, which is gone, and then minus 1/2 g t squared. So what's t? T is 48 over g. Take the square root. So the square root of 48 over 9.8 is 2.21 seconds. 2.21 seconds. It takes this long to drop a parcel or small mail bag that's 24 meters high. That is, I say this is example 8, this is example 9. Next question is, a ball is thrown directly downward. This time the ball already has initial velocity, um, and our acceleration is g, right? So already we have initial velocity, final velocity, delta s, and acceleration. Or we don't have final velocity, I'm sorry. We have initial velocity, delta y, and rg. So we'll use this equation again. It will be negative 30. So this is question 10. Negative 30 is equal to negative 1/2. Right, reason why I have negative 1/2 instead of plus 1/2 at squared is because gravity goes down. So gt squared, and I'm sorry, that's not the right equation. This is not the right equation because there is an initial velocity this time. And the initial velocity is negative 8. Negative 8t minus 1/2 gt squared. So t has to be used, you have to use the quadratic formula, or you can graph on your calculator, which is what I'm going to do. If you have to use the quadratic formula, it's negative b plus or minus the square root of b squared minus 4ac over 2a. But I'm not going to put that down because it's a waste of my time. So I'm just going to graph this equation. This equation's a little bit hard. It's not hard to graph, never mind. I don't know what I'm saying. And what we want to find is we want to move everything to one side, and then we want to find the zeros of the equation. Right, that's what we're trying to find, the zeros of our equation. And if your equation doesn't have zeros, then you've done something wrong. Which I might have done something wrong, which I am a little bit scared. I might have done something wrong. Negative 30. The initial velocity is 8t, so negative 1/2 gt squared minus 8t from a height of 30 meters thrown directly downward. Yeah, I shouldn't be getting this wrong. Oh, wait. Okay, I found out what I did wrong. Never mind. I found out what I did wrong. Okay, zoom 0. Okay, there you go. That makes a lot more sense. 0, go left, go right. What I did wrong was I made 8t plus 1/2 gt squared plus 30, which doesn't have a root, doesn't have a 0. So you want to move everything to one side. You want to put it into your calculator, and you want to make everything basically one side equal to 0, and then graph on and try to find the zeros of your equation. So the time interval is 1.79 seconds. Next, a ball is thrown upward with initial velocity of how much? A lot. Initial velocity of 25 meters per second. At the same same instant, another ball is dropped from a building 15 meters high. After how long will the balls be the same height above the ground? That's a little bit of a hard question, but we can always model the two positions, right? Why position? Because we want to find the same height. So delta y of the first one will be equal to, well, the first one is 25. It has a going up 25, right? So 25 t minus 1/2 gt squared. The second one isn't going up. The second one's being dropped. So delta y is equal to, in this case, it's being dropped from a building 15 meters high. So I think we already know. I think we already know what our delta y is. In this case, we can't keep it as delta y. We actually have to now make it y minus y naught. which is the final velocity, the final displacement minus the initial displacement. Because we already have one of our displacements, we want to find the displacement that it has, where it's going to be the same height as this 25t minus 1 half gt squared thing. So y is equal to, this is not the same. So y is equal to y naught plus vt, or v naught t minus 1 half gt squared. V naught t is 0, y naught's 25, so it's also equal to 25 minus 1 half gt, or I'm sorry, not 25, 15 minus 1 half gt squared. So those are your two equations: 25t minus 1 half gt squared, 15 minus 1 half gt squared. We want them to be the same, so we simply put them equal to each other. Equals 15 minus 1 half gt squared. They're both 1 half gt squared, so we can do this. So time is 0.6 seconds. That is 11. And our final problem that we're going to do today, finally, we're about to be done. I am sick of talking. A student throws a set of keys vertically upward to her sorority sister. I don't know why that's relevant, but sure. Who is in a window 4 meters above. The second student catches the keys 1.5 seconds later. It's the second student, her sorority sister. With what initial velocities were the keys thrown? What was the velocity of the keys just before they were caught? Okay, so we want to find v naught and v. We have a, we have g, and we have t, or delta. We have a is equal to g, we have delta y, and we have time, which is 1.5 seconds. So we could use the second or the third equation. Second or the third equation. The y is negative 4. Or, well, no, the y is positive 4, because y is at the bottom, y naught's at the bottom, y is on top. So we could use any of the equations. Let's use the first equation. No, let's use the second equation so that we can find v naught. V naught, oh wait, I'm sorry, delta y, 4, is equal to v naught t minus 1 half gt squared. So v naught equals 4 minus t over negative 1 half gt squared. Or I'm sorry, I can't do algebra. I actually can't do algebra. 4 plus 1 half gt squared over t, which is equal to what? 4. Oh, I'm sorry. 4 plus 1 half times 9.8 times 1.5 squared divided by 1.5. 10.02 meters per second. And v, what we can use any of the equations to find v, but we're just going to use our third equation. Vt minus 1 half, or in this case it's minus a minus, so because it's minus a minus, our g is going negative, and our v 1 half gt squared in our equation is negative, so minus a minus will give you positive gt squared. So v is 4 minus 1 half gt squared over t, which is equal to, all I need to do is do this and then substitute a negative, and that's giving me a negative number. That is not what I'm supposed to get. Oh gosh, that's giving me a negative number. That's not what I'm supposed to get at all. Let me see how I can resolve this. 10.02 meters. Is it still minus 1 half gt squared? It can't be, because that will be the same as the initial velocity. V 1 half et minus 1 half gt squared. Negative 4, right? Time. Let's change it. Oh yeah, because it is a change in time. Yeah, okay. So the negative is excused because it's a change in time. Divide by 1.5, you'll get you'll get positive 4.68 meters per second. Let's solve it using another method to make sure that we don't get a wrong answer, because getting a wrong answer is a crime in physics. Let's solve it using the v plus v naught, whatever. So 10.2 times 1.5 divided by 2 plus v is equal to 4, which is the fourth equation. So 4 times 2 divided by 1.5, subtract 10.02. Yeah, that still gives me v is equal to a negative number, which is making me very worried now. Okay, I think that's good. Never mind. Okay, that's it for today. If you wanna, I think we'd be able to find another answer if it was a if it was the v squared equals v naught squared. Maybe we would find a wrong answer. I'm not sure. Maybe I calculated v naught wrong. I hope I didn't do that. But that's gonna be it, and I'll see you next time for the second part of this review.